During the last few years, great efforts have been made in many quarters to find better methods of detection and identification of underground man-made explosions. An underground test betrays itself only through the seismic waves it generates. These efforts are therefore closely related to the development of the seismic science. A new line of approach, the use of large seismic arrays, seems to open up new roads. The Norwegian seismic array is, together with LASA in Montana, part of that approach. The wave front generated by any seismic event spreads through the mantle and core of the Earth in a special pattern. A simple but important characteristic of this pattern is the difference in time between arrival of the wave front at different surface points. The installation and operation of a large seismic array was formally agreed upon between the United States and Norway in 1967-68. One had to choose an area with no or little man-made noise. On the other hand, the communication and other supporting facilities had to be fairly well developed. An area within southeastern Norway was chosen. Detailed planning of the array had to take place before starting actual installation in the field. The total array consists of 22 sub-arrays. Each sub-array has one central terminal vault, one long-period seismometer installation in a vault, and 5 short-period seismometers in wellhead vaults. All instruments are connected to the central terminal vault by buried cables. The distance between the short-period installations is 4 to 5 kilometers. One of the major preparations to further planning was to acquire aerial photos of the areas. The aerial photos were examined by geologists for tentative sighting of the installations in the field. The geologists also had the responsibility for field sighting. Red signs are put up to mark the locations. The marking of an approved site was the signal for the building inspectors to start work. The short period installation is in principle constructed as follows. After blasting or drilling into bedrock, the hole is filled with concrete to fasten a vertical steel tube. The tube protects the short period seismometer. On the top of the tube, a steel drum is placed. The drum houses electronic equipment and protects the lead-ins of cables. A concrete vault is erected around the drum. The hole is cleaned after blasting. The geologist measured the depth of the blasted hole for a shallow installation and examined in detail the rock formations and type of rock. The drilling and casing of boreholes for deep installations did not pass without difficulties. Most of the sites were rather inaccessible. In general, the drilling equipment had to be hauled in by tractors. It was a strict stipulation that the seismometers should be placed in bedrock, and thick layers of overburden had to be penetrated at many sites. However, most holes could be drilled at outcrops of the bedrock. The biggest problem concerning the construction of the wellhead vaults was usually the transport of materials to the sites. The bricklaying work was straightforward. Erecting the brick housing might take only a few hours. The brick housing was provided with a wooden frame, which served as support for the protecting lid. The protection cap on the upper end of the casing tube was removed, and the steel drum was mounted. The drum, together with the casing tube, made a watertight unit. The underground vault area in each subarray consists of one central terminal vault and one long period vault. Some of the areas also have a 60-meter short period installation. At the underground vault areas, preparations were made for blasting. Usually the long period vault is partly placed into the bedrock and is later totally covered with overburden. The vault is equipped with 2 horizontal and 1 vertical long period seismometer, each placed in a steel tank. In addition, the long period vault also has a short period seismometer. It is a firm condition that the floor with the instrument tanks is molded directly into bedrock. The central terminal vault is the electronic center of the subarray and houses, analog to digital equipment, data modems, cable terminals, and power supplies to the short and long period single acquisition systems. The central terminal vault is also a subterranean space, and a stairway makes the approach to this vault easy. The power supply is connected to the central terminal vaults. The final construction tasks are backfilling and landscaping around the vaults. One of the aims is to fit the construction naturally to the surroundings. The building inspectors make their final inspection at this point. Access roads used during the construction period receive a finishing touch. Each short period seismometer in a sub-array was connected to the central terminal through buried cables. For this job, various cable-laying equipment was used. Here is a muskeg in action. After the cable is laid, digging of trenches follows. The cable is then placed into the trench. A great number of splices, both for telephone and seismic cables, had to be made throughout the array. The technical requirements to the splices are very high. It is important to protect the wires against dust, moisture and strains. The whole splice is cast in a plastic mass to prevent all motion in the wires at the same time as the splice is hermetically sealed from dampness. Broadly speaking, the aim is to make the splice as enduring as the cable itself. After backfilling, marking of cable trenches is done. At all stages of the project, meetings were held with different advisors. As construction and cable laying were completed for the different sub-arrays, installation of instruments started. The installation began in the middle of the winter, and the work was considerably delayed due to the snow conditions. Next step was to connect the junction boxes in the long period vault to the system. Three long-period seismometers are installed in the long-period vault, sensing Earth motion along the three axes, north-south, east-west, and vertical. In order to differentiate between the north-south and east-west Earth motion, proper alignment of the seismometers is necessary. The calibration of the long-period instruments is a tedious job, mainly due to the fact that a seismometer of this kind has a cycle time of approximately 20 seconds. In order to obtain an absolute value from the calibration, a weight lift procedure is used. When the more advanced testing of the seismometers is finished, the tanks are sealed to reduce the effects from rapid changes in the atmospheric pressures. A short period seismometer is also installed in the long period vault. The rectifier supplies the subarray instruments with DC power. The signal acquisition systems need no manual operating. They are completely automatic. However, some routine inspection has to be done. And since opening of the central terminal vault lid is being detected at the data center for control purposes, the inspector immediately after arrival has to call the data center by telephone. The conversion of signals takes place in the short and long period electronic module, designated as SLEM. The main function of the central terminal vault equipment is to convert analog seismic signals to digital signals, which are transmitted to the data center by the National Telecommunications System. The data center is the brain of the seismic array. The incoming signals are continuously processed and analyzed by computers to disclose if and possibly where a seismic event has occurred. Each time a seismic event is detected, the relevant data are stored for a subsequent and thorough investigation. This classification analysis will hopefully answer the crucial questions whether the seismic event was a natural earthquake or a man-made explosion. Another important task for the data center is to control the performance and calibration of the field installations. Sophisticated and highly automatic data processing equipment is installed in the data center. For a rapid check of the recording and analysis results, devices for visual inspection of processed data are available. One of these devices is a plotter, which may write out recorded seismic signals. Interesting seismic events are discussed by seismologists and other experts. The Norwegian seismic array is an experimental research installation to test the feasibility of the large array concept, and will also serve to increase the art of seismic science in general. Together with other similar installations, it may form a basis for a worldwide monitoring system for a possible extension of the Test Ban Treaty of 1963, which does not include underground tests.